Okay guys, good afternoon. Before we start our lecture today, we want to continue to transistor applications. Okay, before we start our lecture today, some of your friends request an example questions and circuit of BJT saturation. Okay, so this video and slide is purposely show to explain more about the saturation in BJT and one examples on BJT saturation. Okay, so we start now. Saturation region. When base emitter become forward bias, IB will increase, so will IC, and VCE will decrease as result of RC. When VCE saturated, base collector become forward bias and IC cannot increase, even IB increase. Once IC maximum, transistor is said to be in saturation, and by Ohm's law, IC saturated is equal to VCC RC. Okay guys, previous slide is from previous lecture. Before we go deeper about saturation in BJT, first you have to understand what is the difference between forward bias and reverse bias. Okay, now slide show two circuits to differentiate between forward bias and reverse bias. Forward bias is a condition that allow current through the PN junction. So when you allow current through the PN junction, voltage will be zero. Okay, so diode is forward bias when a voltage source is connected as shown in A. So the positive terminal of the source, the positive terminal of the V bias is connected to the anode diode, okay, through a current limiting resistor. Okay, dia nak limitkan, you want to limit the current through the diode, so it put a current in a resistor, and the negative terminal of the source is connected to cathode. Negative terminals of V bias, the voltage source is connected to cathode. The forward current IF is from anode to cathode. So this is the direction of the currents as indicates. Okay, so the forward voltage drop VF due to the barrier potential is from positive at the anode to negative at the cathode. So this for bias. While reverse bias is the condition that essentially prevent current through the diode. So I is equal to 0. A diode is reversed when a voltage source is connected as shown in this figure. The negative terminals is connected to anode side of the circuit, and the positive terminals is connected to the cathode side of diode. A resistor is not necessary in reverse bias because it is shown for circuit consistency. The reverse current is extremely small and can be considered to be zero. Okay, so notice that the entire bias voltage V bias appear across the diode. Okay, so I equal to 0. Here, I equal to forward current. For forward bias, diode is closed circuit, while in reverse bias, the circuit is open circuit. Okay, the ideal models of a diode is the least accurate approximations and can be represented by a simple switch. So when the diode is forward biased, it ideally acts like a closed switch or close or on switch. Okay, short circuit on switch. The diode is assumed to have a zero voltage, okay, a zero voltage across it when a forward bias, and the forward current is determined by the bias voltage V bias and the limiting resistor R limit using Ohm's law or Kirchhoff law. So IF equal to V bias over R limit. Okay, now when the diode is reverse bias, it ideally acts like an open circuit or off switch. Okay, open circuit I equal to 0. The reverse current is assumed to be 0 and the reverse voltage equal to the bias voltage. So VR, V bias, VR voltage across the diode is equal to V bias. Okay, now cutoff and saturation can be illustrated in relation to collector curve by a load line. Ideal cutoff is IC equal to 0, IC equal to 0, and VCC equal to VCE equal to VCC. So here is the cutoff point. And saturation when IC equal to IC saturations and VCE equal to VCE saturations. In between cutoff and saturation along the load line is active regions of transistor operations. Okay, now using a circuit like that shown in figure, a set of collector characteristic curve can be generated that show how the collector current IC varies with the collector to emitter voltage VCE for specific value of base current IB. Okay, so how IC, okay, varies with the collector emitter voltage VCE when IB for specific value of IB. Okay, so that's how we want to show the collector characteristic curve, okay, by using IC, VCE, and IB. Okay. Okay, notice in the circuit diagram that both VBB, VBB and VCC are variable source of voltage, and we assume that VBB is set to produce a certain value of IB and VCC is 0. So for this condition, both the base emitter junction and the base collector junctions, base emitter and base collector junctions are forward biased because the base is approximately 0.7, VCE equal to 0.7, while the emitter and the collector are 0 volt. The base current is through the base emitter junction because of the low impedance path to ground, and therefore IC is 0. When both junctions are forward biased, the transistor is in the saturation region of its operations. Saturation is the state of a BJT in which the collector current has reached a maximum and it independent of the base current. So IC is reached a maximum and independence of the base current. So any increasing of IB, the value of IC is still same. So that's the mean of independent of the IB current. As VCC is increased, okay, in figure B, as VCC is increased, VCE increase as the collector current increase. So as VCC is increased, okay, VCC is increased. So I see okay, once again, as VCC is increased, VCE increase as the collector current increase. So the collector current increase, VCE increase, collector current pun increase. This is indicated by the portion of the characteristic curve between point A and point B in figure B. So point A and point B is saturation region. So IC increase as VCC increase because VC is remain less than 0.7. So here, as long as VCE is less than 0.7, here, okay, IC still increase. So this due to the forward bias based collector junctions. Okay, so ideally when VCE exceed 0.7 at point B, the base collector junction become reverse bias and the transistor goes into the active or linear region of its operations. Okay. Okay, now for examples, find the VCE, VBE and VCB in the circuit of figure 1A. Determine whether or not the transistor are saturated. So this is NPN transistor with RB equal to 3.9K, RC 180 ohms, VCC 15 volt, VBB 5 volt, and beta DC equal to 50. Okay, now this is the list of equation for NPN transistor where VBE is equal to 0.7, VBB minus VBE equal to VRB, where VRB is equal to IBRB, VCE equal to VCC minus VRC, where VRC equal to ICRC, and IC equal to beta DCIB, and VCB equal to VCE minus VBE. So given from figure, VBB equal to 5 volt, VCC equal to 15 volt, RB equal to 3.9K, and RC equal to 180. So the question is find VCE, VBE, and VCB. So VBE obviously 0.7 volt. So form 3, VCE equal to VCC minus ICRC. So IC equal to beta DCIB, and IB from 1, okay, from 1, IB equal to VBB minus VBE over RB, where RB is equal to IBRB. Okay, now IB equal to VBB minus VBE over RB, where VRB equal to IBRB, So is equal to 5 VBB 5 minus VBE 0.7 over RB 3.9K. So IB equal to 1.1 milliampere. So IC equal to beta DC IB, where beta is 50, IB 1.1 milliampere. So IC equal to 55 milliampere. Therefore, VCE equal to VCC minus ICRC, where VCC equal to 15 minus IC 55 milliampere and RC 180. Therefore, VCE equal to 5.10 volt. So from 6 equation from previous slide, VCB equal to VCE minus VBE. So 5.1 minus 0.7, therefore VCB equal to 4.40 volt. Okay, the next question is that determine whether the transistor is saturated or not. Okay. What is saturation? Saturation happens when IC reach a maximum value, or we call as the IC saturation. So how we want to determine IC saturation? We assume VCE saturation is equal to 0. So now IC saturation is equal to VCC over RC. So given VCC equal to 15, RC equal to 180, therefore IC saturation is equal to 83.3 milliampere. Okay, now from previous calculation, we have determined that IC is equal to 55 milliampere. Okay, so this collector current characteristic curve. Okay, now B is the Q point, where saturation point. So here IC value is equal to 83.3 milliampere, and we say here is the saturation points. Where is the location of IC saturations, or the maximum value of the IC? Okay, now our IC value is 55 milliampere, less than IC saturations. Okay, so therefore the transistor is not saturated. The transistor is not saturated because the value of IC is less than IC saturations. Okay, guys.